Okay, so we have as our starting point momentum space broken up into these shells of modes. Okay, now what we're going to do is we're going to follow a three-step procedure, which we will then repeat. And using these three steps, we'll eventually manage to integrate over all of the modes in momentum space, which is what we want. So let me define for you this three-step procedure. So we've got three-step procedure. Okay. Procedure. Okay. So what is the three-step procedure? So in the first step, we isolate the outer shell of modes in momentum space. So what are these modes? Well, the modes that we're going to isolate are the ones sitting in this last shell here. So let me just color this in red. So we've isolated out those shells. And let me tell you how we do it, okay? So we do the following. We take our field phi, and we're going to decompose it into one field that I'll call phi less than of k, plus another field that I'll call phi greater than of k. And what does this look like? Well, phi less than of k will be equal to phi of k if the magnitude of k lies between 0 and 1 minus b lambda, and it's equal to 0 if the magnitude of k lies between 1 minus b lambda and lambda, okay? And then the field phi greater than, well, this is 0 if we lie between 0 and 1 minus b lambda, and it's phi of k if we lie between 1 minus b lambda and lambda. So what have we got? These are the inner shells, and this is the outer shell, okay? And we will always imagine that b is very much less than 1, okay? Now, you might wonder exactly what b is, so let me tell you what b is. Well, let's take a magnification of a piece of this picture. So this piece, so I've magnified it here, and here is the red shell. The red shell is sitting over here. What B is the size of this shell. So that size there, that size of the shell, that's what B is. So that's how to interpret B. It just sets the size of this shell, and all of these different shells have exactly the same value for B. So B is some constant parameter. Good. Okay, so that was pretty easy. We just separated out a shell. So this was the first step, okay? That was step number 1. Now, let's talk about step number 2. So for step number 2, we integrate over a shell. We integrate over a shell. And what I have in mind is that we might be trying to calculate some correlator just constructed only out of the phi less than modes. So what would this correlator be equal to? Well, it'll be an integral over d phi greater than. it will be an integral over d phi less than. We'll have our modes. And we will have the action. Now we want to do the integral over the phi greater than. So let's define this. Let's put the d phi less than here. That's the integral we're not going to bother doing. We can take all of these modes, the phi less than modes, they don't depend on phi greater than at all. And then we'll have the integral over d phi greater than, and we'll have e to the minus s. So that's the only thing that we have to integrate over phi greater than. And this will give us the integral d phi less than of x1, phi less than of xn. And let's call the answer from doing this integral. So the answer from doing this integral, we will call e to the minus s effective, okay? So we've generated a new action, an effective action. This is the action that will govern the lower energy modes, okay? And to give you an idea of the sort of scales in this picture, we might imagine the following. So this is energy. So let's put here mod k. We've got the cutoff over here, so that's lambda. Here is naught, and then there's some low energy scale here, and inside here we have particle physics. So this is where particle physics operates, and what we want to do is we want to integrate out all of the shells sitting over here. We'll slowly integrate shell by shell, move down to here until we get to particle physics. And when we do this, you can see that we're going to keep generating a new action. When we keep generating a new action, the mass in the new action will have changed a little bit. The couplings in the new action will have changed a little bit. So we talk about the parameters of the theory will flow. We will flow down to low energy by integrating out these shells. So as we integrate out the shells, we flow down to low energy. Great. So that's step number 2. We integrate over a shell. Then let's take a look at step number 3. So for step number 3, in step number 3, we compare S and S effective. So we want to see how did the couplings change, how did the mass change, and all of that. There's a subtle point here, so that's why we actually have to do something. There's a subtle point. S and S effective are defining two integrands. So take a look. Look at this line over here. This is where S appears in integrand, and this is where S effective appears in integrand. Notice that in this first line, we integrate over phi greater than and phi less than, and in this bottom line, we only integrate over phi less than. So what is the subtle point? What we actually want to do, we want to compare two integrands. You can see that S and S effective are defining two integrands. Well, this only makes sense. It's only a fair comparison if the domains of integration match. Okay, so only if you're integrating over the same things does it make sense to compare the two integrands. We will manage to get the two domains of integration to match by rescaling the momenta. Okay, And we're going to do this in detail, but let me just tell you the idea. So we've integrated out that last shell. So our onion in momentum space got slightly smaller because the last shell's missing. Then we're going to rescale it, boom, to pop the onion back to where it was. So that's the rescaling that we're going to do. And we're going to compare S and S effective after we've pushed the onion back to the size that it was. Okay. So we'll need to just rescale the cutoff by a little bit so that we still have the same domain in momentum space. Good. So those are the three processes that we will follow. Once you've done the 3 steps, you could then repeat and do the 3 steps again. And so get rid of one more shell. And you could keep repeating this until you get rid of an enormous number of shells and then ultimately get to low energy. During this process of keep on repeating these 3 steps, you are going to flow to low energy. All of your couplings will change. All of the parameters of your theory will change. You'll keep changing your action. But by the time you get to a very low energy, that's the action that describes the low energy physics. It'll be an effective action because we have summarized all of the physics of the high energy modes in the parameters that appear in the low energy theory. And that's why it becomes an effective theory. Now, one very nice way to visualize this is that you can think of the space of all theories. So what is the space? So this is the space of all quantum field theories, okay? So all of the quantum field theories we can build for our free scalar field. So what would the axes in this space be? So there'd be an infinite number of them. I've only drawn 3 of them. Well, one of the axes might be m squared, the value of the mass. Another axis might be the value of the 5-4 coupling lambda. Another axis might be a coupling that allows 6 fields to interact, a lambda to the 6. But each different axis in this space would be a different coupling. And then we would start at some position at this space. So this is where we start. And now we start to repeat our 3 steps where we keep integrating out shells, separating shells, integrating out shell, then rescaling shell. And what we will find is we will follow some trajectory inside this space of all possible theories. So that's what this 3-step procedure will do. And we're interested in working out where we move, how this trajectory winds through the space of all possible theories. So we want to perform these 3 steps, and we just want to keep performing them. Actually, step number 1, separating out one shell of modes, that's really easy, trivial to do exactly. Step number 2 is hard, actually integrating. We have to perform a path integral over phi greater than. How are we going to do it? Well, we know how to do path integrals. We use Feynman diagrams. So this is the step where we'll be using Feynman diagrams again. So everything that we've learned so far will be employed to achieve step number 2, sorry. And then step number 3 is again easy. It's just going to be some rescaling to make sure that the integration domains match. Great. Okay. We're nearly ready to start calculating.